Yeah, so I'm going to give a talk on a zkCNN. Yeah. So I specifically asked Gigi to move my, my talk right after Kai because it is just to give you a brief overview of how the zkCNN works. It is essentially a sum check and a combination of GKR itself. So that's why I thought like giving a talk on zkCNN might be better after Kai. So for the first section, I'm just going to give you a brief introduction into AI and how the image recognition on the neural network works. And I'm just going to dissect by what actually works, like what mathematical operation that the CNN or neural network does. And then I'm going to link that into how it converts to the sum check and the GKR itself. So yeah, so just to give you a brief overview of neural network used in image. So this is a very high-level overview how the neural network works. So to recognize an image, you first need to extract the features from an image. So for example, if you want to recognize if it is a dog or a cat, you might want to recognize a subpart of an image, whether you want to detect an eye of a cat or an ear of a cat, or you want to detect a cat dog's eye or some hairs. So that's where the feature extraction comes. And if you get enough feature extracted from the image, then you can put it into a classification layer, which is basically a matrix multiplication of the flattened feature matrix or a feature vector. And so how do we extract the features? And this is where the convolution layer comes in. So convolution layer, what it basically does is an extraction of the features. It aggregates the features within a fixed size of window, and the window slides by a stride or one by one on the image, and convolutes the values of all the pixels within an image. So just to give you a brief overview how the convolution works. So you have an image that looks as a matrix, and the orange window convolves all the values in the within the window, and you get the convolved feature, which is smaller than the image that is actually the input to the neural network. So how this works is, suppose you have 4x4 matrix, that's an input, and you have a kernel or a filter that is going to convolve your features to a 1 pixel. So for the first example, you want to make a dot product between an input and a kernel, which is 40, and you construct by every elements, every windows that you can make in an image. So at the end, you get that 2x2 matrix, which is an extracted feature. And the second part is probably the pooling layer. This pooling layer is in charge of selecting an important feature. So even if you have a convolved feature, you want to pick a representative element. So suppose you have like some background, you have some other objects that might be very random, but if you want to detect a cat, you might want to detect something that is very important within a cat, such as like shape of a fur or pointy ears. That is what you want to extract, and that's what the pooling layer does. And there are two methods. You want to get an average within the window, or you want to get the maximum within the window. So how this works, if you have a pooling layer, you have an input, and you want to output the maximum value within the window. So it's a 2x2 window for the 4x4 image. You get an output as in the right-hand side. So this is like very high overview, probably more friendlier to the ZK engineers. So you have a convolutional layer, and then activation layer, and then pooling layer. and you put that into, you stack that up into multiple layers, and that is why it's called like deep learning, because you have a lot of repetitive matrix multiplication or matrix operation over time. And if you have enough CNNs stacked in your neural network, then you're going to have a fully connected layer that is going to do the final task, such as like classification or whatever you want. So, and the challenges of proving the CNN is that, as you can see, there are many dot products. For this example, if you see the input dot the kernel, you're going to make a matrix multiplication gates for every dot products that is within the image and the kernel. That is going to create a lot of gates. And if you take the naive approach, if you construct a circuit for all convolutions within the image and the kernel, the complexity of layer is going to be n squared times w squared, where n is the image of the size of the image, and w is the width of the window, and that is times d, which is the depth of the entire neural network. So we want to optimize the convolution by fast Fourier transform, because the naive approach usually takes like two polynomials, and you want to like get the multiplication of two polynomials, which creates all the inefficiencies. But if you convert that into a pointwise coordinates using the fast Fourier transform, it allows the convolutions to be much more efficient than just naively multiplying two polynomials. So the big question here for the zkCNN, we need to make the proof of the dot product, which is a polynomial multiplication efficient, which also is a problem of making the fast Fourier transform efficient. So yeah, so do every one of you know what fast Fourier transform is? Because I didn't know. All right, let's skip that. Yeah, so yeah, just to give you, it's just a brief overview of like how coefficient of representation, the complexity of like operation for the coefficient representation. The addition is O to the n, and probably what we're interested is a convolution or multiplication, which is O(n) squared. And point value representation, the multiplication is O(n). So it is obvious that the point value representation is much more efficient if you're doing convolutions. So we want to get the best of both worlds. So as you can see, we have two polynomials here. We want to evaluate into a point value representation. And if you do the point value multiplication, that's going to be O(n). So the entire operation is going to take O(n) log n. So because it's asymptotically closer to O(n) log n. What we are trying to prove is probably the FFT. And we want to choose the like a smart value for this entire matrix multiplication. So suppose you have some random points on A0, A1, A2, and Y0, and you want to choose a value for X that is going to make the matrix multiplication much more efficient. So if we set the X to the roots of unity at M, so roots of unity is the complex number W omega, such that the power of omega is 1. And so since the complex number is periodic, or so the power of like omega to the m makes it periodic. And if you convert that into a table, I mean, giving the representation how the FFT looks like in the matrix multiplication, you get this kind of matrix. And then, so since the omega n is periodic, you can actually reduce the computation count, because now that you have like repetitive numbers, you don't have to compute for all like the whole entire fast Fourier transform matrix. You just have to compute like at most n computations of the omega values of omega. Yeah. So yeah. So I think this is where my presentation probably ends. So the conversion of fast Fourier transform to a subject protocol is probably what I needed to, what I should be talking about. But I think that's as far as my presentation goes. So just to give you a brief overview how it works, I'm still in the progress of reading it. So you want to represent this into a sum check using where the f is a fast Fourier transform and c is the coefficient of the polynomial. And then you want to represent this as a multilinear expression. And the whole paper is about how to make a sum check protocol, like FFT and sum check protocol, more efficient. And there are many like equations. I could just write it down, but since I don't really have like a very deep understanding of like all the components, I don't think I'm in the position to give you like higher level understanding of zkCNN. But like, I think for the next talk I should be prepared.
For next week.
Yep. Thank you.
I think it is easier to use average pool instead of max pooling, average pooling, because compute a maximum number of vector kind of not easy in the circuit, right?
Yeah, that's right. But as an AI engineer, there are many papers about like different like pooling layers. Yeah. But like max pooling layer is probably the best like proven to work. So like I think I'm not meaning like we should use the max pooling layer. Yeah. So I think there should be a trade-off between what kind of like deep neural network you're going to build and what kind of trade-off you need to make for the zk itself. I think that's one of the part we can make some trade-off. Mm-hmm.
Any idea if you could apply this just as well to transformers, or it's a whole beast entirely?
The transformers. So I think the transformers is also a lot of like dot products. Yeah. So it's not really a convolution, but it's a lot of dot products. So as the zkCNN tells you, it's not really about the CNN itself. It's more about like how to optimize the dot product itself. So if you manage how to improve the dot product itself, I think it's also going to work for this case as well.
Yeah, that would be great.
Mm-hmm. All right.